Okay, so we started our discussion of orthogonal polynomials by looking at from a generic perspective and looking at some abstract way of writing down properties, and then we also started looking at Hermite polynomials and we wrote down some of its properties. In this lecture, we will continue our discussion of Hermite polynomials and look at some more properties along the lines suggested by the general approach. Okay, first is to work out the differential equation which is satisfied by Hermite polynomials. To do this, we will use the prescription we wrote down a few lectures ago. So the idea is to look at this quantity. So we managed to argue that if you take 1 over w of x and take the derivative of this complicated looking object, w times s times the first derivative of these, the polynomial of degree n. In fact, you're going to get back the same polynomial subject to some constant factor, right? So we will work out this differential equation for the Hermite polynomial, and specifically we will compute this lambda, right? So first of all, we must plug in w of x is equal to e to the minus x squared. That's the weight function corresponding to Hermite polynomials. S of x is just 1, right? So it goes all the way from minus infinity to plus infinity. So S of x really does not have a role here. So all we have to do is work out this quantity. So this gives us an e to the x squared times the first derivative of this quantity e to the minus x squared times the first derivative of hn of x must be equal to some lambda times hn of x. But what this lambda is, we will work it out explicitly here, right? So expanding, we have so if you take a derivative of this product, right, so I mean s of x doesn't appear, so if just a derivative which is the product of two of these functions, it's going to give you minus 2x times e to the minus x squared. This e to the minus x squared will cancel with this e to the minus x squared in the denominator, so you just have a minus 2x times the first derivative of hn of x. Or alternatively, if you just treat e to the minus x squared as a constant, which cancels with this e to the minus x squared in the denominator, then you have to take the second derivative of hn. So that's the second term. So minus 2x dhn by dx plus d squared hn of x by dx squared must be equal to lambda times hn of x, right? So we will work out this coefficient lambda, and it turns out that to get this, we have to use these two recurrence relations that we already derive for the Hermite polynomials. And so the way to get to equation 1 from here is to take a derivative of this first equation, right? So to start with this first equation and take a derivative with respect to x. So you have d by dx of hn of n plus 1 of x must be equal to 2 times hn of x plus 2x times dhn of x by dx minus 2n derivative of hn minus 1 of x d by dx of hn minus 1 of x. But when we look at this equation, it's in suggestive form. We see that ultimately we want to write every term in here in terms of hn, right? So in order to do that, we will make use of the second recurrence relation. Now in place of dhn plus 1 of x, we can write it as using this 2 times n plus 1 times hn of x, right? So we want only one kind of polynomial in the whole equation, and that's, you may have different orders in the derivatives taken, but we want to just work with just hn of x. And so indeed hn plus 1 derivative is going to become hn according to this relation, but you have to be careful with the factor, and so in fact you get 2 times n plus 1 times hn of x. And again on the right hand side, we see that this term and this term, they both involve hn of x, so we leave these two terms as it is. But this term has an hn minus 1 of x, which we don't want. We want to write the whole equation in terms of just hn, and in order to do that, once again we invoke this result but in the other direction. So we see from here 2 times n times hn minus 1 of x is actually nothing but d by dx of hn of x. So we have 2 times n times d by dx of hn minus of x, which is basically like taking the derivative. If you take this equation and take a derivative of both the left hand side and right hand side with respect to x, you get this term really, which is on the right hand side. So in place of 2n dhn minus of 1 of x divided by dx, we simply write down minus d squared by dx squared of hn of x, invoking this result. So which is really the differential equation we are after, because if you rewrite this, you can rewrite it as d squared hn of x by dx squared, you bring it to the left hand side, minus 2x dhn of x by dx plus, so you have 2 times n plus 1 minus 2, which becomes just 2n plus 2n hn of x. So you see that this equation is really the same as, you know, this form that we had from the general prescription was this one. So we have, you know, this term is here and this term is here, and indeed it is equal to lambda times hn of x, but we know what lambda is from, we have computed it here. In fact, lambda is minus 2n. Okay, so this equation is in fact probably familiar to a lot of students you know, taking this course. I guess we have seen it in a quantum mechanics course and maybe elsewhere as well. So one familiar context in which this appears is when we are solving the Schrodinger equation for the harmonic oscillator potential. So the way you solve the Schrodinger equation for the harmonic oscillator problem is, you know, there are two different ways. One is this Schwinger's way, which is a clever algebraic approach, and then there is this sort of bread and butter differential equation approach, which involves writing down a power series expansion and then trying to find a power series solution after you have peeled out, right? So you start with this wave differential equation for the wave function itself, and then you argue that, you know, your wave function must fall off in a nice way, right, for large positive x and negative x, and then you work with a differential equation of another quantity, which basically gives you this kind of an equation, right? So, and then in fact this 2n that you get, you know, lambda equal to minus 2n is really you know, the condition that you have for ensuring that you get polynomial solutions for you know, such a differential equation, right? So, and that is essentially the same as the quantization condition for the harmonic oscillator problem, right? So the harmonic oscillator problem, well, I mean, in general, the differential equation corresponding to the harmonic oscillator problem can be solved, right? So from a mathematical point of view, you will definitely find solutions. There will be power series solutions. It's just that these power series are not going to have nice enough properties that you can give them and the interpretation of a wave function, right? So they would blow up at plus x and minus x. It's only when you impose this, what is really a quantization condition, so this forces the energies to have certain allowed levels. When you have these special levels of energy, lambda equal to minus 2n, then in fact you are able to normalize your wave function, which basically means that you get polynomials. Your power series solutions, you know, the power series truncates, and you get in fact just a polynomial, and those polynomials are nothing but these Hermite polynomials. So in fact, you could have actually also viewed this this as a kind of an eigenvalue problem, right? So I guess it's even more transparent if you look at this equation. So you have some stuff, some operator acting upon hn of x is equal to some lambda times hn of x. So hn of x has this interpretation of an eigenfunction for this eigenvalue problem, and lambda is an allowed eigenvalue, right? So hn of x has to be, if hn of x has to be a polynomial, then lambda must take only these allowed values. So when you do this, in fact, you can write down the general wave function for the nth excited state of the harmonic oscillator, and this is probably a familiar expression. So you have this overall, you know, e to the minus x squared type fall off. I mean, in suitable units, you have to put in all these numbers, these constants which come from the mass and natural frequency and so on. And once again, the Hermite polynomial is sitting here, and you have this overall factor outside. Okay, so so this is often a starting point, right? So in fact, there are many discussions of Hermite polynomials which start with a differential equation of this kind, and then work out the properties of when do you get a polynomial, and then you say, okay, they have a sequence of polynomials, they're all orthogonal, and then you work out recurrence relations and so on. But I mean, the method we have followed is to start with from an abstract point of view, and then now we are in fact obtaining the differential equation as sort of a consequence of the the property of these polynomials. Okay, let's look at another aspect of the story, which is the so-called generating function. So it turns out that you can actually stitch together these polynomials, Hermite polynomials, along with a very carefully designed set of coefficients, and form a series like this. So t to the n divided by n factorial, n going from 0 to infinity, hn of x. It turns out you can actually write a closed form expression for this, and that's this object, e to the 2x t minus t squared. So in order to show this, we have to simply show that if you take the nth derivative of this function with respect to t and put t equal to 0, you get hn of x, right? So if you can show this indeed, then this is the generating function, and this can often be used to prove many of the results. We have already proved some of these results in, like the recurrence relation, for example, right, starting from the Rodriguez formula and so on. But in fact, you can, this generating function often provides a very clever way of proving many properties of various polynomials involved, various orthogonal polynomials involved have different generating functions, and starting from here, it's a method by which many properties can be extracted. But first, let's for the Hermite polynomials, let us show that indeed this is the generating function, and basically which boils down to showing that the nth derivative of g of x comma t at t equal to 0 will give you the Hermite polynomial. So let's argue for this using induction. So there is a way to argue for this directly from the Rodriguez formula as well, which perhaps you would be encouraged to try and work out on your own. But let's argue for this using induction. So first we observe that this is true for n equal to 0. So that means if you don't take a derivative but simply put t equal to 0, you get 1, right, which is definitely the first member of the Hermite polynomial sequence of polynomials. H0 of x is indeed 1. And again, we can also verify for the first derivative. If you take dg by dt and put t equal to 0, you get h1 of x, because dg by dt is nothing but 2x minus 2t times e to the 2xt minus t squared. And now if you put t equal to 0, you simply get 2x, which is indeed the next member of the Hermite polynomial class of polynomial. So now suppose we assume that this result holds all the way from 0, 1, 2 and all the way up to k, where k is greater than 1, right? So now by induction we will show the result holds, and in order to do this, we have to show that if 0, 1, 2, 3 all the way up to k, where k greater than 1 is true, then we will argue that it's also true for k plus 1, and therefore it will be true for the next one and so on. So by induction, this result will hold for all these coefficients in this expansion, right? So how do we do this? So we consider the k plus 1th derivative with respect to t of this function g of x comma t at t equal to 0, which is the same as taking the kth derivative of the first derivative of g, dg by dt, right? But now what is the first derivative of g, which is actually nothing but 2x minus 2t times e to the 2xt minus t squared, right? So which you just start with this function and take 1 for the first order derivative, and that's nothing but 2 times 2x minus 2t. So it's a little bit like here, but you don't put t equal to 0, so you just leave it as it is. And then now you argue that you see, as far as, so this is a sum of two terms, and this 2x basically has nothing to do with this derivative with respect to t. So 2x can come out, so I can write this as 2x times the kth derivative with respect to t of just g of x comma t, because after all this is nothing but g of x comma t at t equals 0, and then minus 2 times 2 can come out, but t cannot come out, t has to stay, the kth derivative of t times g of x comma t at t equals 0. Now, but the first term we observe that this is actually nothing but, this is nothing but at t equals 0, it's nothing but, you know, because we have this induction result, it's nothing but 2x times hk of x. And once again, this I will argue now in a moment, we can show that this is nothing but 2 times k times hk minus 1 of x, right. So so this is how do we argue for this? Okay, let's go back to this original result. So what we have, the induction hypothesis is that g of x comma t is equal to summation over n going from 0 to infinity t to the n times some coefficient, like if I call it Cn, but basically we have argued that the Cn is equal to Hn of x divided by n factorial for the first, you know, k terms, where k goes from 0, 1, 2 all the way up to k. So now if I multiply this by t, so then I have t to the n plus 1 divided by n factorial, right. So I'm not giving you all the steps, this is something that you should convince yourself is true. So if I take t times g, it's t to the n plus 1, and then I multiply the denominator and numerator by n plus 1, so I have n plus 1 times t to the n plus 1 divided by n plus 1 the whole factorial hn. Then I can do the shift, so I have this n plus 1, in place of n plus 1 I put in, I don't know, so let me redefine n plus 1 as m. Then I have m times t to the m divided by m plus m minus 1, sorry, h m minus 1, and then I have a m factorial. So basically it's going to look exactly like what you have here, except that you'll get an h m minus 1, and then there will be an extra factor of m sitting here. So that's what I'm saying will boil down to this minus 2k times hk minus 1 of x, right. So this is a consequence of the induction hypothesis, where we have assumed this is true for all these integers starting from 0 to k, and then we use that result in the original form of expanding this, and then now finally we argue that this is actually nothing but h, I should explicitly write this down, h hk plus 1, hk plus 1, hk plus 1 of x, which is really a consequence of one of the recurrence relations, right. So we had this recurrence relation, we saw this earlier. So we have hn plus 1 of x is 2x hn of x minus 2n hn minus 1 of x. So this is just a property of the Hermite polynomial. So if you take this combination of Hermite polynomials, indeed this is hk plus 1 of x. So we have managed to show that if you have this induction hypothesis, then the next term in this sequence is also the Hermite polynomial. Therefore this result holds, right. So which therefore by the principle of mathematical induction, indeed hk of or hn of x is the nth derivative of g of x comma t at evaluated at t equal to 0. So indeed the function we have given here, this equivalently this is the generating function for our Hermite polynomial. So I mean you could have worked this out directly from first principles, starting from the Rodriguez formula, right. So that is also something that I'll urge you to work out, this alternate way of seeing this. And so what is the the reason to go after such a generating function is because it can derive many properties for you. So it's a powerful tool and in fact we could have used the generating function to derive these two recurrence relations. We derived it from other methods starting from the Rodriguez formula, but in fact if you just use the generating function, it's very quick to obtain these results, right? So which we will assign as part of homework. Okay, so that's all for this lecture. Thank you.